dear students, physics practical ਦੀ ਇੱਕ ਹੋਰ ਬੜੀ ਹੀ interesting class coefficient of sliding friction and coefficient of viscosity ਵਿੱਚ ਤੁਹਾਡਾ ਸਾਰਿਆਂ ਦਾ ਸਵਾਗਤ ਹੈ। ਇਹੋ ਜਿਹੀਆਂ audio visual classes ਰਾਹੀਂ ਅਸੀਂ ਤੁਹਾਨੂੰ experiments ਕਰਨ ਦਾ correct way ਸਿਖਾਉਣਾ ਚਾਹੁੰਦੇ ਹਾਂ। ਅੱਜ ਦੀ ਇਸ ਕਲਾਸ ਵਿੱਚ ਅਸੀਂ ਤੁਹਾਨੂੰ ਦੋ experiments ਸਿਖਾਵਾਂਗੇ ਜਿਨ੍ਹਾਂ ਵਿੱਚੋਂ ਪਹਿਲਾ ਹੈ to study the relationship between force of limiting friction and normal reaction and to find the coefficient of friction between a block and a horizontal surface. Friction ਦੀ ਸਾਡੀ ਲਾਈਫ ਵਿੱਚ ਕੀ ਇੰਪੋਰਟੈਂਸ ਹੈ ਇਸ ਨਾਲ ਤਾਂ ਤੁਸੀਂ ਸਾਰੇ ਹੀ ਵਾਕਿਫ ਹੋ। ਆਓ ਇਸ ਬਾਰੇ ਥੋੜਾ ਸਾਇੰਟਿਫਿਕ ਵਿਊ ਨਾਲ ਵੀ ਗੱਲ ਕਰ ਲਈਏ। ਡੈਫੀਨੇਸ਼ਨ ਤੋਂ ਸਟਾਰਟ ਕਰਦੇ ਹਾਂ। Friction is a force that opposes motion in a particular direction. It occurs when the surfaces of two materials come in contact with each other. It has already been pointed out that friction appears because of the interaction between the charged particles of two bodies near the surfaces of contact. Any macroscopic object like a steel plate or a wood piece has irregular surface at atomic scale. A polished steel surface may look plain to unaided eyes, but if seen under a powerful microscope, its surface is found to be quite irregular. This figure shows qualitatively how an apparently plain surface may be at the atomic scale. When two bodies are kept one over the other, the real area in contact is much smaller than the total surface area of the bodies. The distance between the particles of the two bodies becomes very small at these actual points of contact, and the molecular forces start operating across the surface. Molecular bonds are formed at these contact points. When one of the two bodies is pulled over the other, these bonds are broken. The materials under the bond are deformed and new bonds are formed. The deformation energy appears as the increased random motion of the particles of the bodies. The bodies thus become heated. A force therefore is needed to start the motion or to maintain the motion. The maximum static friction that a body can exert on the other body in contact with it is called limiting friction. This limiting friction is proportional to the normal contact force between the two bodies. We can write F maximum equal to mu s into n, where F maximum is the maximum possible force of static friction, n is the normal contact force, and the constant of proportionality mu s is the coefficient of friction whose value depends upon the nature of material and the roughness of the two surfaces in contact. Let me also tell you something very interesting related to friction. Dust, impurities, surface oxidation, etc. have a great role in determining the coefficient of friction. Suppose we take two blocks of pure copper, clean them carefully to remove any oxide or dust layer at the surfaces. heat them to push out any dissolved gases and keep them in contact with each other in an evacuated chamber at a very low pressure of air. The blocks stick to each other and a large force is needed to slide one over the other. The coefficient of friction becomes much larger than 1. If a small amount of air is allowed to go to the chamber so that some oxidation takes place at the surface, the friction coefficient reduces to usual values. ਹੁਣ ਅਸੀਂ ਆਪਣੇ ਅੱਜ ਦੇ ਫਰਸਟ ਐਕਸਪੈਰੀਮੈਂਟ ਨੂੰ ਪਰਫਾਰਮ ਕਰੀਏ। ਇਸ ਐਕਸਪੈਰੀਮੈਂਟ ਦਾ ਆਬਜੈਕਟਿਵ ਹੈ to study the relationship between force of limiting friction and normal reaction to find the coefficient of friction between a block and a horizontal surface. We will need some apparatus to perform this experiment. These apparatus are a wooden block with a hook, a scale pan, some thread, a horizontal plane with glass top, a frictionless pulley, a weight box, a spirit level, and a spring balance. चलो ਹੁਣ देखिए कि इस experiment ਦੀ theory ਕੀ है। The magnitude of the limiting force of friction is directly proportional to the normal reaction. If Fms is the magnitude of the limiting friction and R stands for normal reaction, then we have Fms upon R equal to mu, where mu is the coefficient of friction. Let us now come down to the procedure. Start with cleaning the glass surface of plane and then adjusting the surface of plane. Also ensure that the pulley is frictionless. Find out the least count and zero error of the spring balance. Measure the weight of the wooden block and the scale pan on the spring balance, keeping the zero error of the spring balance into account. Take 3 pieces of suitable length of thread and tie their one end to scale pan and the other end to the hook of the block. Pass the thread over the pulley, placing the wooden block on horizontal plane. Put some weight in the scale pan and tap the glass surface gently. If it does not slide, go on increasing or decreasing the weights in the pan till the wooden block just begins to slide. You may have to add, remove, or change the weights a large number of times till you can make your wooden block slide with slight tapping. The weight of the pan and weights in the pan, when combined together, give the force of limiting friction. The normal reaction R is given by the weight of the block W. Now place a known weight P on the block so that normal reaction R now becomes equal to W plus P. Now repeat all the steps that you took for the block without the weight by adding more weights in the pan. Repeat the process by putting 3 or 4 more different weights on the block so that 5 or 6 different sets of observations are taken. Now give a careful look at the observations to be noted and record them in the same order. Note down the number of divisions between 100 gram weight and 200 gram weight N of the spring balance. Then find the least count of the spring balance, that is equal to 100 gram weight upon N. This is in gram weights. Check and note the zero error of the spring balance E in gram weight. Then find the zero correction of the spring balance C equal to minus E in gram weight. Find the observed weight of the pan small w dash in gram weight. Corrected weight of the pan small w equal to small w dash plus minus C in gram weight. Observed weight of block W dash in gram weight. Corrected weight of block capital W dash equal to capital W plus minus C in gram weight. Make an observation table like this and thereafter plot a graph between FMS and the normal reaction R. Consider the normal reaction along x-axis and the limiting friction along y-axis. Choose an appropriate scale to do that. After you join all the corresponding points plotted, the graph must appear as a straight line. And then is the turn for making the calculations. The coefficient of friction can now be calculated by finding the slope of the straight line formed in the graph. In the example set here, mu is equal to FMS upon R equal to 41 upon 100, that is equal to 0.41. The result is to be written like this. The straight line graph shows that the sliding friction FMS is proportional to the normal reaction R. Also, mean value of coefficient of friction is equal to 0.41. In order to get a good and accurate result, we must follow these precautions for this experiment. The pulley should be frictionless. The portion of thread between pulley and the hook should be horizontal. The weight in pan should be increased in small steps. Tabletop should be tapped gently each time. The spring balance should be suspended from suitable stand while weighing the block. The zero correction should be determined and taken into account. The sources of error that can hamper the result of this experiment are: the tabletop may not be horizontal, the friction at pulley tends to give more value of coefficient of limiting friction, the thread part between block and pulley may not be horizontal. The second experiment that we have on our cards for today is to determine the coefficient of viscosity of a given viscous liquid by measuring terminal velocity of a given spherical body. Well, may I quickly brush up your knowledge about viscosity before teaching the details of the experiment. See, when a layer of a fluid slips or tends to slip on another layer in contact, the two layers exert tangential forces on each other. The directions are such that the relative motion between the layers is opposed. The property of a fluid to oppose a relative motion between its layers is called viscosity. The forces between the layers opposing relative motion between them are known as the forces of viscosity. Thus, viscosity may be thought of as the internal friction of a fluid in motion. If a solid surface is kept in contact with a fluid and is moved, forces of viscosity appear between the solid surface and the fluid layer in contact. The fluid in contact is dragged with the solid. If the viscosity is sufficient, the layer moves with the solid and there is no relative slipping. When a boat moves slowly on the water of a calm river, the water in contact with the boat is dragged with it, whereas the water in contact with the bed of the river remains at rest. Velocities of different layers are different. Let v be the velocity of the layer at a height z from the bed, and v plus dv be the velocity at a height z plus dz. Thus, the velocity differs by dv in going through a distance dz perpendicular to it. The quantity dv by dz is called the velocity gradient. The force of viscosity between two layers of a fluid is proportional to the velocity gradient in the direction perpendicular to the layers. Also, this force is proportional to the area of the layer. Thus, if F is the force exerted by a layer of area A on a layer in contact, then F is proportional to area A as well as proportional to dV by dz, or F is equal to minus eta A into dV by dz, where the constant of proportionality eta is called the coefficient of viscosity. The negative sign is included here as the force is frictional in nature and hence opposes relative motion. The coefficient of viscosity strongly depends on temperature. Finally, coming down to the experiment now. The objective of this experiment is to determine the coefficient of viscosity of a given viscous liquid by measuring terminal velocity of a given spherical body and to plot a graph between terminal velocity and square of the radius of spherical body. Let us see what apparatus is required for this experiment. A half-meter high, 5 centimeter broad glass cylindrical jar with millimeter graduations along its height. Some transparent viscous liquid, which can be castor oil or glycerin. 5 steel balls of different radii. A screw gauge, stopwatch, thermometer, and a clamp with a stand. Let's now know a brief theory behind the experiment. When a spherical object is allowed to fall through a viscous liquid, the weight of sphere acting downward is given as 4 by 3 pi r cube into rho into g, where rho is the density of sphere. The upward thrust equal to weight of liquid displaced by sphere is given as 4 by 3 pi r cube into sigma into g. where sigma is the density of liquid. The effective downward force mg is equal to 4 by 3 pi r cube into rho into g minus 4 by 3 pi r cube into sigma into g, or mg is equal to 4 by 3 pi r cube into the difference of rho and sigma whole into g. Now, upward force of viscosity is equal to 6 pi eta r into v. When downward force is balanced by the upward force of viscosity, the body falls down with a constant velocity called terminal velocity. Thus, 6 pi eta r into v is equal to 4 by 3 pi r cube into the difference of rho and sigma whole into g, from where eta can be calculated as 2 by 9 into rho minus sigma into g whole into r square upon v. Now, get ready to understand the procedure. First of all, clean the glass jar and fill it with the viscous liquid, which must be transparent. We have chosen castor oil for this purpose. The vertical scale along the height of the jar must be clearly visible. Note its least count also. Check that the spring of the stopwatch is tight enough. Find its least count and zero error if any. Next, arrange the 5 steel balls in order of their increasing radii. Calculate the least count and zero error of the screw gauge and determine the mean radius of the first ball. It will be good if you mark 2 convenient full division readings on the vertical scale of the jar. You can see the upper reading marked by a paper strip A and the lower reading marked by a paper strip B. Then drop the first ball gently in the liquid and start the stopwatch as soon as the ball reaches at the mark A. And now watch its fall. Be very careful and stop the stopwatch just when the ball reaches the lower convenient division at B. Calculate and note down the distance fallen and time taken by the ball. Repeat the same steps for each of the other balls also. Be sure that you keep the distance fallen same in all cases. Finally, note and record temperature of liquid, which is 22 degrees Celsius in this case. Ultimately, you should have these observations noted in your record file. Least count of the vertical scale in millimeter, which is 1 millimeter here. Least count of the stopwatch, which is 0.01 second here. Zero error of stopwatch in seconds, which is 0 seconds for this case. Pitch of the screw gauge H, that is equal to 1 millimeter here. Number of divisions on the circular scale is equal to 100. Least count of the screw gauge then becomes equal to 1 upon 100 equal to 0.01 millimeter. Zero error of the screw gauge E in millimeter if any. If there is a zero error, then note down the zero correction of screw gauge C equal to minus E in millimeter. Well, there is no zero error in this case. Temperature of liquid in degrees Celsius, which is 22 degrees Celsius for this case. The observation table for measuring the terminal velocity has to be made like this. We'll now calculate r square by v from the graph also. Plot a graph between r square and v, where r square is taken along x-axis and the terminal velocity v is taken along y-axis. An appropriate scale is to be chosen before you do that. Mark the points and join them. The graph should be a straight line. Take point A and B on the straight line. From A and B, draw AC and BD perpendicular on x-axis. From B, draw BE perpendicular to AC. Then V by r square is equal to slope of spherical line AB equal to tan theta, which becomes equal to AE upon BE equal to VA minus VB divided by RA square minus RB square. Thus, using the value of r square by V in the formula for coefficient of viscosity, we can write the value of eta in CGS units, that is, in poise, which is 9.83 poise in the relevant case. The result is to be written as the coefficient of viscosity of liquid at temperature 22 degrees Celsius is equal to 9.83 poise. Let's have a look at the precautions regarding this experiment. Liquid should be transparent to watch motion of the ball. Balls should be perfectly spherical. Velocity should be noted only when it becomes constant. The most probable sources of error are: the balls may not be perfectly spherical, the liquid may not have uniform density, the recorded velocity may not be constant.
Dear students, finally, have a quick glimpse of some common questions for you. My first question is, how do you reduce the friction in pulley in the experiment? The answer is by oiling them. The next question is, on what factors does the value of mu depends? The answer is, it depends upon the nature of the surfaces in contact and the condition of the surfaces. Another question is, what are the dimensions of coefficient of viscosity? The answer is, the dimensions of coefficient of viscosity are ml minus 1, T minus 1. Another question, define viscosity. And the definition is, the property of a fluid to oppose a relative motion between its layers is called viscosity. ਮੈਨੂੰ ਉਮੀਦ ਹੈ ਕਿ ਤੁਸੀਂ ਅੱਜ ਸਿਖਾਏ ਗਏ ਦੋਨੋਂ ਐਕਸਪੈਰੀਮੈਂਟਸ ਦਾ ਪੂਰਾ ਲਾਭ ਲੈਣ ਦੇ ਨਾਲ ਇਹਨਾਂ ਨੂੰ enjoy ਵੀ ਕੀਤਾ ਹੋਣਾ ਹੈ।
ਅੱਜ ਦੇ ਲੈਸਨ ਤੇ ਧਿਆਨ ਦੇਣ ਲਈ ਤੁਹਾਡਾ ਧੰਨਵਾਦ। ਅਗਲੀ ਕਲਾਸ ਵਿੱਚ ਹੋਰ ਨਵੇਂ ਟੌਪਿਕਸ ਨਾਲ ਫਿਰ ਮਿਲਾਂਗੇ। ਗੁੱਡ ਬਾਏ ਐਂਡ ਗੁੱਡ ਲੱਕ।